we introduce it.
Yes, I can start.
Yes, you may start. Oh, before Semi may introduce the Professor Dąbrowski.
Professor Dąbrowski is from University of Szczecin, and is that the correct pronunciation in Polish?
Yes,
Professor
Szczecin.
Dąbrowski, and he's here to give us a talk on a class of generalized Fermat equations of signature 2, 2, and 3.
Okay.
Let's welcome him.
Okay, thank you very much. Hello to everybody. Thank you very much. I would like to thank very much Professor Ikeda for inviting me to give a talk on this seminar. In my talk, I will report on our results joined with Karolina Chałupka and Gohan Soidan. So hello, Gohan. And the results concern a very special class of generalized Fermat equations of the signature 2 to n3. And most of these results are now published in Journal of Numbers Theory online. And the second part will be published, I think, soon. It is still in preparation. So next, yes, I will. Some very brief introduction. So short overview of the proof of Fermat's last theorem. The proof is usually now explained that there are 4 steps for the proof. So first, take prime equal or bigger than 5. And assume that we have non-trivial solution to the Fermat's last theorem, ABC. Such a solution will assume that A is congruent to 3 mod 4 and that B is even. And then we can, first step, we can associate a 3-type elliptic curve. We can calculate global discriminant. We can calculate the conductor. In particular, such a curve is semi-stable. We can associate to such or every elliptic curve over the rationals mod P Galois representation. And in this case, such a representation is irreducible for any prime P equal or bigger than 5. And let me mention that there is very deep result of Mazur that if we consider any elliptic curve of the rationals, then the corresponding representation mod P is irreducible for any prime P bigger than 163. So it's very general, but in special cases, irreducibility can be proved for smaller primes too. And of course, generalizations are known now. So in the case of number fields, but I will, in my talk, I will use only elliptic curves over the rationals, so I will not discuss the general case. The next step is modularity, and of course, the first general case was that semi-stable elliptic curves over the rationals are modular. It was proved by Weiss and Tyler. So elliptic curve is modular on the level of representations, mod P, associated mod P representations modular. And the last step is Ribet's level leveling theorem, which implies that such a representation arises from some new form of weight 2 and level 2. It's contradictions because there are no non-trivial new forms of such weight and level. So it's very brief. It's proof, well known. No? Of course, modularity is known for every elliptic curves over the rationals. It's not only over rationals, but over other number fields, in particular of the totally real, but it's not for us. I will not use it. Okay, so maybe first generalizations. Take note the Fermat transform, but consider one coefficient which is prime L, say, then if L is equal to 3, 5, or 11, the same method gives non-trivial solution for all. There exists no non-trivial solution for all primes different from L, because in this case all the steps are the same, and the last step, Ribet's level leveling, leads to the contradiction because there are no non-zero form. But in general case, consider equation star when L is any odd prime, say, or power of prime. It is more subtle case, and now of course Ribet's level leveling leads to the space of new forms of weight 2 and level 2L. But if L is different from 3, 5, or 11, then there exist new forms. There are some new forms, and for such new form, we need to show that corresponding that mod P representations associated to Fourier curve and to the existing new forms are not isomorphic. So it can be proved if L is less than 31, or L is neither Mersenne nor Fermat prime, and for primes it may be proved for primes sufficiently large. It's a result of Serret-Mazur, and explicit constant was calculated as well by method of Duet-to-Krauss. We can make it explicit. So it's a kind of asymptotic Fermat result. And for the case where prime L is 31, we can prove that the equation has non-trivial solution for primes belonging to some arithmetic progression. So for positive proportion of primes. The same for other, for many cases, other cases, still in the signature PPP, it is the same powers. And say, take for instance L equal to 15, or take two coefficients, 3 and 5, different, and many others. So we can prove such results of type that no solutions for positive proportion of prime exponents. It's in general, we can use so-called symplectic methods invented by Krauss and Halberstadt. And some few words in a general, very general situation, fixed non-zero integers, big A, B, and C, and fix also positive integers P, Q, and R, such that some of on the left-hand side, so sum of its inverses is less than 1, then the general Fermat equation 1 has only finitely many primitive integer solutions. So it's well known now. And how to solve? Of course, it's generally know that at most finitely many solutions, maybe no non-trivial solution. But how to prove it? Modern techniques coming from Galois representations, Muller forms of Frey-Elegage curves, or some Frey type abelian varieties, variants of Ribet's level leveling theorem, of course, modularity of HDFS or abelian variety over rationals or other number fields will will apply it. We can apply it, but it's still we can prove that the corresponding equations. We can find all the solutions only for a very limited number of signatures, and usually only when the product of ABC is small, or radical of the product is small. Yes. And good introductions, resultant reductions to the subject. Yes, papers by Bennett, Chen, Tachman, Yazdani, Bennett, Mihailescu, 6 seconds, survey of noun. Yes, of course, it's not the very recent results because it's a very active area. Yes. And let me mention that when the sum of inverses is close to 1, but it's less than 1, of course, then one needs the modular methods are not enough. Of course, modular methods are not enough. It's usually very subtle. Yes, we need more and more sophisticated methods. But here, if the exponents are small, we can use or combine Chabauty type methods. Yes, its refinements. Yes, so it's just like it. In my talk, I will discuss a very special class of different equation of signature 2, 2, and 3. Such a equation, so it's equation 2, was studied first by Bruin, Chen, Dachman, Bennett, Chen, Dachman, Yazdani, in very special cases. It is known that such a equation has no solution for a family of primes congruent to 5 mod 6. Moreover, a Krauss type criterion is known, which allows to check non-existence of solutions for all prime exponent in a large interval. And let us mention that the case n equal to 7 was deduced only from a more general result of Punen, Schäfer, and Stoll. So it's a combination. There was a combination of Chabauty type method and modular techniques. And in my talk, I will discuss generalization of this the above different equation, where we take C equal to 4 and product AB is basically 7. That's actually not families, but only 2 curves, only 2 equations. So it's written here. Yes, so 2 families of different equations. It's partly it is because the class number of the corresponding imaginary quadratic field is 1. Then it's easy, but of course we may try to generalize it when say the class number is not divisible by 3. So it's similar techniques may be applied. So, but anyway, I will discuss only the case of this. These are for these very few values of A. So I will show very soon that will be easy that only for A equal to 7 we may expect non-trivial solutions. Yes, because simple simple observations that for the 5 remaining values there are no solutions, not trivial. As here is some formulation first that what we can do. Of course, I will repeat it in some 20 minutes. The same as some introduction. In particular, we will formulate cross-type criterion and use magma to prove the following theorem that For the differential equation 3, with 8 equal to 7, we have the following result. The non-existence of trivial solutions. Of course, p equal to 7 is excluded, and also p equal to 13 is excluded. Maybe it's unexpected, but the modular techniques at the moment were not able to exclude it. As for the any exponent, we have the following result using so-called symplectic method and quadratic reciprocity. So it's for two methods give two answers, but together we had the following theorem that no solution for this different equation for a positive proportion of primes. So it's exactly for primes belonging to one of these arithmetic progressions. Let me start with some preliminaries. So the key will be the following. Starting first step number 0. So it will be lemma 3. So we consider factorization of the left-hand side of our differential equation in the imaginary quadratic field. Then we obtain the following lemma. What is important here that important is expression for y to the power n in terms of so-called number of u and v. Is for the 5 is for the first of the differential equations, 6 is for the second. So it's pair off. So it will be used permanently. And first application is very easy. It's the following corollary that if we take a 11 and so on, 163, so 5 values, then the differential equations 3 and 4 have no solutions. It is easy when you use the above lemma, that is recalled, and consider reductions modulo 8. So this left-hand side will congruent to 0 mod 8, while the right-hand side will be congruent to 4 mod 8, so a contradiction. But the same in the second case. So in fact, we will consider only two different equations. I will consider the prime exponents usually bigger than 7 separately, and small exponents separately, because here we need another method, usually not the modular techniques. So let me start with the first equation. So in this case, again, using the lemma, previous lemma, are reduced to the problem of solving the equation, different equation for y to power p u times to the quadratic form. Yes, with odd uv, and of course y is also odd. Yes. Okay, so here the graded common divisor of the two factors on the right hand side can be 1 of 3. So then, as a consequence, obtain two different equations, so led to the two different equations of signatures to P2. So it is written here. So if d is equal to 1, led to such different equation 7, and if greatest common divisor is 3, then you obtain the different equation 8. So please note that here we have fixed coefficient 1 minus 4.1, while in the second equation we have the first coefficient is not fixed, a radical is fixed. Coefficient depends on the exponent. Yes. So we'll try to solve these two different equations. So first, let us start with the first one. Here it is easy. The answer is almost complete. In this case, we can apply famous Bennett-Skinner strategy, even for a more general equation. When prime is bigger or equal to 7, here, of course, we can calculate levels of the corresponding uniforms. We need to eliminate two possible levels, and in the case of the first level, there are 13 Galois conjugation classes. We have to eliminate. In the second one, it will be 39, as I remember. And we follow, yes, we will calculate system of eigenvalues, and we follow the paper by Bennett-Skinner. All what is necessary is proved, so additional some necessary results of lemmas or propositions are taken from the Bennett-Skinner paper. So here are some details, of course, details for this second level in the paper published in Journal of Numbers. Now let us consider the second different equation. Here the situation is much more difficult. Again, we can start because such a question is of signature 2pp2, so we can try to use Bennett-Skinner strategy, but of course it is not enough. So at least we can consider the Frey type curve is constructed in the paper. So calculate global discriminant, conductors, and of course apply level layering. So we obtain two possible levels. So obtain two spaces of new forms, weight 2 and level, two possible levels. But in this case, unfortunately, the situation is much more subtle because, in fact, there exists isomorphism, that mod P Galois representation associated to the Frey curve is isomorphic to some Galois mod P representation associated to some of the elliptic curves associated by modularity to the new forms. The same is here. So it's, we need to consider, yes, some additional available tools. So one of these tools will be, in general, symplectic method. But first, let us consider the case of small fixed and small, so prime exponent in some interval, yes, up to some 10 to the power 9. So it's what is called Krauss type algorithm, Krauss type criterion. So here, and using it, we can prove such a result. And let me say a few words. What is the Krauss type criterion? It was stated about 20 years ago by Krauss in his paper in another situation. So this criterion is a variant of his criterion. Such type criterion exists for some other types of defining equations. It's not very new. So let us say a few words. So take consider prime Q and positive integer k, such that k is divisor of Q minus 1, and because as Q is prime number, so we can consider field FQ and consider a group of kth roots of unity in the multiplicative group of such a finite field. And with our defining equation and such a k, we have associated some subset of the root of unity in such a finite field. And for each member of such a set, we associate elliptic curve over a finite field FQ. And then we can of course consider Frobenius trace. And Krauss criterion is the following theorem in our situation. So we need only to eliminate two elliptic curves. Of course, actually 4, but because for the remaining pair of curves, squares of the traces of Frobenius are the same, so it's enough to consider only one pair. It is because we need only squares of Frobenius traces, so it is better. So assumptions are as follows: assume that Q is prime for some positive k, that square of Frobenius of the for any f, as we have only two f's, is not congruent to forward p, and it's and the last assumption is that squares of traces are not congruent, where the second trace is trace associated to the curve over finite fields. So for any element from the kth rows of unity, subset of its unity, we need such assumption. If we have if such assumption is satisfied, then we can prove that the definite equation has no solutions in coprime of integers. Let me mention that such a criterion, Krauss criterion, is a generalization of a classical Sophie-Germain criterion in the case of Fermat's last theorem. Classical, but here is of course to a very, very big generalization of this method. So we were able to use such criterion, of course, to prove such a theorem, use such a criterion, and prove that there are no non-trivial solution for this definite equation in the range from 11 to 10 to the power 9, excluding two primes, 13, 17. So maybe it is interesting how large k were taken. So in our calculations, we were restricted to k less or equal to 500. Yes. We tried for these two primes, p, 30, 17, take higher values of k, but were not successful. So one idea was to refine this criterion. Indeed, here is formulation is what is means refined. So two extra conditions are added, yes, so must be satisfied by digit case. So in this case, we were able to exclude, yes, to prove that for prime power, prime exponent 17, there are no non-trivial solution, but this refined criterion doesn't imply that the different equation with p equal to 13 has no non-trivial. So it's still it's such a criterion probably still needs to be refined, yes, further, but we're stopped at the moment. It's not, yes. So here is additional, because in order to prove result, there's no non-trivial solution for the original equation, we need to consider the case of prime exponent 19. But it was done, yes, by the variant of this criterion. So, yes. Okay. So it is, now let us consider the question for which prime exponent we can prove that there are no non-trivial solutions. We expect that for all there are no, but it seems that it's not possible at the moment to prove such a result by any available methods. So we can prove using so-called symplectic method that this different equation has no positive solutions for a positive proportion of primes, is more precisely for primes such as belonging to such arithmetic progressions. Here is some details I will probably not make any. So maybe a few words. If we have two empty curves, so E will be, say, free curve, E prime will be curve, empty curve coming, yes, related by modularity to some weight 2 and some level empty curve, yes, related to by modularity to some new form, yes, of weight 2 and level, some level. And assume that P-torsion models are isomorphic. Then there is additional structure, so we can say that such isomorphism is symplectic or antisymplectic. And if we start with with some elliptic curve, then all, in fact, if the representation of such elliptic curve is irreducible, then all isomorphisms have the same type, or all some symplectic type. All are symplectic isomorphism or antisymplectic. So it's, I will not define precisely, because here I want to show that the proof is depends on very explicit criterion for symplecticity. So here's a paper by Kraus and Freitas. And of course, using and another paper will be necessary. I will use another paper in the proof, and the result is as follows. The idea is that we have symplectic isomorphism between the mod P representation of free curve and two of the curves which we have. Yes, here 4 curves. There are symplectic isomorphisms with 2 of these, So because we can prove that all isomorphisms are symplectic. Yes. But we can use another criterion to show that in some cases for some primes, the isomorphism is anti-symplectic. So we obtain a kind of contradiction for some primes there. So then we can prove that for such primes there is no non-trivial solution. Yes. So it's there is no this kind of contradiction on the level of symplecticity of isomorphism of Galois models. Yes. And another method is sometimes works, and it works in our situation too, gives another set of primes for which there is no non-trivial solution. Is this, so call it. Another method uses quadratic reciprocity in terms of Hilbert symbol, and such a result, very useful here, was proposed, was proved in the paper by Bennett and co-authors about 5 years ago, or maybe 7 years ago, published 5 years ago. And here is some details. So if we fix some non-zero rational numbers R and S, and assume that the following differential equation has a solution in prime non-zero integers A, B, C, that the B, C is odd, then we have a relation for the corresponding Hilbert symbols. We can use it, yes. This lemma, and of course, such lemma is not sufficient, but we can combine such lemma and modular methods to prove the following result. Again, that no solution for positive proportion of primes. Very explicit. Okay. Now let us consider the second of our different equations. So the first, let me call it the first different equation was 7x to the square plus y to the 2n squared to the 4 at the end. Now it's 7 different, not a different place. It's the only change, but results are different, and such a question is more difficult to describe the solutions. So we conjecture that all non-trivial solutions to the title equation, all non-trivial solutions are therefore obvious solution for obvious ones. We can prove that here only under the ABC conjecture. So assume that ABC conjecture, then for positive proportion of primes, all the non-trivial solutions are the obvious ones. Yes. Here, of course, we can start again with the lemma on the second page, part 2 of the lemma, and reduce the problem of solving the title equation to solving the following equation, and in fact to solving two different equations of signature to P3. Here is one of them, 11. In this case, we have four obvious solutions, plus minus 1, minus 1, plus minus 1. This solutions leads to the obvious solutions of my different equations. And we conjecture that these are all, but why we're not able to prove? Firstly, let us mention that under ABC conjecture, one can prove that there are no that these are the only solutions for primes sufficiently large, so it's asymptotic Fermat type, yes, for under ABC conjecture, yes. And we can prove that there are no natural solution when B is congruent to one mod for, but if B is congruent to three mod for this big abstraction, yes, it's probably no available methods will give the set of solutions. So it's yes, we are not able to eliminate all the new forms in this case. The problem is that the remaining new forms to eliminate were without complete multiplication. So the second question is the following 12. In this case, we expect that no material solutions exist, and here we can use symplectic methods, this similar way as before, and prove that this question has no questions, no solution for positive proportion of prime exponents. And for small, for prime exponents belonging to this interval, we can prove that no natural solution at all, without any exceptions. And now let us consider small exponents. So here will be first and second pairs of different equations. In the first case, it is very easy because the question concerning non-trivial solutions is reduced to the rational points on the corresponding LT curve. And such a curve has trivial modified group. That's the proof. And in the second case of this question, again we can reduce the problem to the rational points on some LT curve here, but this time such a LT curve is non-trivial cyclic modified group. And we can find a generator, and in fact we can write down infinite family of points, yes, on the curve, and solutions or different equations also can be described explicitly. At least we can show that belongs to some infinite subset. Of course, it's infinite set of solutions. There's a more precise description. Now let us consider the case of n equal to 4. And first let us consider the case of n equal to 2. So it's, in this case, it is additional information, so we need only the shape of these for y, yes. So here, more exactly, this realm parameterize all triples of integer solutions, the co-prime integers, yes, satisfying such a solution. So here we have x, y, and z are given by described in terms of two parameters, rational parameters c and t, and we'll use expressions for y or for y square, yes, because next page. So again, so in particular, what we'll use is that we obtain the following for genus 2 curves, and the problem, non-trivial solution to our different equation is reduced to finding a fine rational points on these for genus 2 curves. But it is easy because we can consider points to edic. Turns out that there are no fine points in two edic fields. Yes. So we may use magma comments to check it. So this is very easy. Now let us consider the second theorem, the second different equation. So again, we can write down, we can parameterize all the solutions or the triples for the different equation. 8 is replaced by 4 and use it to produce 4 genus 2 curves. And the problem again is to reduce to find all rational points, fine rational points will produce non-trivial solutions to our different equations. Here, for the first of these curve, we can find all the solutions very easily. So considering theoretic points, so there are no such. For the last two, it is a bit more difficult, but easy because we can use magma. So first, for the curve C7, rank of the Jacobians 1, and we have explicitly written point of infinite order. So you can use Chabaut and produce the complete set of solution of rational points. In the second, for the last curve, it's even easier because Q rank of the Jacobian is 0. So again, it is given by magma, and so we have all solutions. So it's for example, one different solution. But the remaining curve C6 is more difficult to calculate rational points of such a curve. At the moment, we're still trying to find all. What we know is that there exist 6 such points, including 2 points at infinity. To actually that these are all points using magma in calculations. This magma shows that there are no other with height bounded by 10 to 8. And why we are not able, because rank of the Jacobian Q rank is very probably 2. It's between 1 and 2, it's not decided. It's not a standard Chabat method to calculate it, will not work. We're trying to elliptic Chabat, but it's still not successful. Let me mention that by the Chabat Coleman estimate, we obtained that there are at most 8 such points. So 6 is known, 8 are the 8 have. It's not so far. So if we collect all the rational points on these 4 curves, then we can write down all the solutions to the original different equation. So here are 12 such solutions. If there exist 2 more points, there will be 4 more solutions, but I expect that no more. That is all. Now let us consider the exponents 5 and 7 for the first different equation. Exponent 5, so n5 says it's easy because here we are led to consider 2 genus 2 curves, and in each case Jacobian has rank 0, and we can use Chabaut to obtain no defined rational points. So no non-trivial solutions to the original different equations. The case of n equal to 7 is more difficult. We don't know at the moment how to solve it. So the modular method doesn't work alone. Chabaud-type approach, it is valid to two genus free cars, and we're not able to find that rank of Jacobian is probably 1, but we were not able to find any point of infinite order. So it's not done by this method. But very probably that there's the hope that using the methods of the paper Kuhn, Schäfer-Stoll, we can prove that the following more general different equation, we can find all solutions to this different equation, then deduce what we want in our situation. But it is, yes, no, difficult. Probably we'll do it, but not, it's not done at the moment. Now let us consider the second different equation. Here first let us consider several primes starting from 7. So here is theorem. Not all theorem depends on this proposition. Such proposition is almost proof, is not finished yet. I hope that all will be finished, and proof of the proposition we use the so-called Chabaud method as reduced by Stoll. And why it is enough to prove proposition 32? It is because we know, yes, proof of this theorem, Saint-Hilaire is reduced to solving two different equations here. And Krauss-type criterion can be used to solve the second one. So we need only to consider the first one different equation, but this leads to such hyperelliptic curves. And noted that we have 3 obvious rational points, which leads to the obvious solution to different equations, and our task is to prove that these rational points are all rational points on such algebraic curves. And case of experiment 5, so here we expect there are exactly 8 non-trivial solutions. The first 4 are the same, but here are 4 additional solutions, and these additional solutions will come from the rational points on the second genus 2 curves. So here again we are reduced to consider 2 genus 2 curves. Yes. But in this case Jacobian, these 2 curves have 2, and standard Chabaud method doesn't work. And today we may try to use another variance of Chabaud or combination. I don't know. Okay. So here are some references. Okay, so thank you very much for your attention. Thank you. Hello? Sorry?
Okay. Thank you, Professor Dąbrowski, for his excellent talk. Any question? Unfortunately, your voice only the only problem was that your voice was very low. but I'm so grateful for your excellent talk.
Very sorry for that, for technical. So most of the results are written, yes?
Yes, yes, no problem. We enjoy that. Thank you.
So I hope I am in time, yes? So it was not too long, yes. Some questions?
Okay. Are there any questions? If it's not,
Okay,
I have a simple question. In page, at the first page of your lecture note,
first page, yes?
in a theorem that you have an exception for p equal to 13. And I'm curious about what is the reason for this exception? I mean,
13. Okay.
yes,
Because,
what is the exception for 13? Yes.
yes, because first exception was moment. Yes, first exception was 17. Yes, we were able to remove
Yes.
this exception
Yes.
by defining the Krauss type algorithm, but we were not able to refine it further to remove this remaining prime. So it's probably can be done, but we are not. Yes. So it was at the moment we're not able. Yes, because it's more and more assumptions. I don't know. Probably it's possible.
Okay, thank you. And I have another question. Does work your method for other imaginary quadratic number fields? I mean, for those that have not class number 1.
Yes, as I mentioned at the beginning, that I think that we can try to repeat all these, yes, so decomposition, and I think that if we assume that the class number of the corresponding imaginary quadratic field is not divisible by 3, then the same method will work. But of course, more and more, yes, it will be less precise results, but I think that it will work. Yes.
Okay, it's interesting. Thank you. Are there any questions? If not, you may unmute your microphone and join me for encourage again Professor Dąbrowski.
Thank you very much.
For his excellent talk. I'm so grateful for him for accepting to have a talk in our joint seminars. And thank you everyone for attending. I hope to see you again at 2 weeks later from now, where Dr. Amir Qadir Marzi will be the next our expert, and the details will be announced through our Google group. Thank you again. I just want Semi for stop the recording and